get those numbers. So the number of moles per liter. Okay, per liter. So what do you mean by that? So if you take a chemical, say A, and you take 1 liter of the chemical A, and just look at how many moles of A are in that 1 liter of what do you call chemical. Okay, 1 liter of the reactant. So you take 1 liter of A and see how much moles are inside there. And what are the moles? So mole is equal to 6.02 into 10 raised power 23 molecules. Avogadro's number actually. Okay, so this is what really is there. Alright, so now the concentration of this particle, what happens with the concentration of this particle? So when this chemical reaction is happening, these A and B put together will mysteriously, that we know from the chemistry, will be turned into what you call the product C. So in other words, these two will go away and produce what you call C. In other words, the concentration of A and B over the time will decrease and the concentration of C will increase actually. Okay? So the concentration of A and concentration of B will decrease over the time. Okay? The quantity, the number of moles over the time during the reaction, the concentration of A and B will decrease and the concentration of C will increase actually. Okay? So if I want to, for example, know, so here's an interesting thing that I would like to know. So I want to know how the concentration of C is increasing over the time. Then I need, so this would be what you call the average rate. Okay, so you can say this is really the average rate of reaction. Average rate of reaction. Okay. What is average rate of reaction? The way concentration of the product is changing over the time. So obviously this is going to increase and these two are going to decrease. Okay. So the concentration of C, how the concentration of C is changing over the small amount of time is really the average rate of change. And if you talk about, say, 2 instants, then the concentration at time T2 minus the concentration at time, say, T1 divided by T2 minus T1. So this is going to be the average rate of reaction between instants T1 and T2. So what would be the rate of reaction? In other words, the instantaneous rate of reaction. The instantaneous rate of reaction is going to be how much of reaction, how much of A and B is turning into the C at any time, say for example T, is going to be what? Is going to be, if you take for example limit at delta T goes to 0 and delta change in the concentration of C with respect to T, and you can call it, denote it by Tc by dt. Okay. So what are some observations about this? So how the rate of change in concentration, another interesting question would be that how the rate of change in concentration is related with the rate of change in concentration in A and rate of change in concentration in B actually. Okay. So what will happen during the reaction? So during the reaction, so this is an abstract reaction, okay, so not particular reaction. During the reaction, the concentration of the product will increase actually. The concentration of the product will increase. In other words, if you look at say dC by dt, it will be a positive number. And if the concentration of the product is increasing, and then the concentration of the the reactants A and B would decrease actually. And dA over dt and dB over dt will be negative. These will be negative. Okay. Now the question is how they are related. So I'm going to say, in other words, the rate at which the concentration rate is increasing, concentration of C is increasing, how that rate is related with these two rates. So the way the concentration, say the rate of reaction is going to be d by the concentration of C equal to, so obviously these rate of reactions are going to be equal. In other words, if this is A is decreasing, simultaneously A is the concentration of A is decreasing, simultaneously A of concentration of C will increase. But how much increase? It will increase as much as A is decreasing. And if the concentration of B, so so what will happen over the reaction? The concentration of B will decrease and the concentration of C will increase. But how much concentration of C will increase? It will increase as much as the concentration of B is decreasing. So you're going to say that these all rates are equal. Okay? The rate at which the concentration of C is increasing is equal to the rate that at which the concentration of A is increasing, and the rate at which the concentration of B is decreasing actually, and all of this is equal to rate of reaction. But we have to be careful. So one thing that is silly here is that this is a positive number while these two are negative numbers. So how they can be equal? So I need to put a minus here. Minus here. Minus here. Okay? So now, so this is already negative, multiplied by minus is going to be, what do you call, give you the positive number dC by dt. Okay? So this is really the formula for the rate of reaction for this reaction. But if you are talking about, for example, a generic reaction, so imagine you have the A molecules of reactant A and B molecules of the reactant B, and they all together produce, say, C molecules of the reactant C. So small a, b, c are the number of molecules of the reactants in product. Okay. Then how they will be, or maybe I can add, say, so it can also happen that there are more than one products actually. There are two products, and imagine that the D molecules of D are being produced. The question is, what would be the rate of reaction now? The answer is, these two will decrease, so the concentration of A and B will decrease, and the concentration of C and D will increase, okay? But their rate would be equal. The rate at which they are decreasing and increasing are going to be, what do you call, equal, and but they are going to be related in similar way. So I can say the concentration of A by dt, okay, is going to be equal to what? Minus 1 over A. So like minus there, but now you have 1 over A, okay, because you have A here, and minus 1 over B, concentration of B with respect to dt and equal to 1 over C. So these two are going to be positive, equal to 1 over D, and concentration of D with respect to what they call dt. Okay? So in other words, if you have sum of rates given to you, or at least you know one of the rates, then you can determine the entire rate of the reaction. You can determine the the rates at which the other reactants and products are decreasing at. So if you know one of the quantity, this or this or this or this, you can determine the rest. Okay, so they are just going to be multiple of each other. So that's, for example, is one of the model that people use, for example, in chemistry to determine the rate of reactions. Another example from the chemistry is this. It's called the thermal compressibility. Another example from, say, chemistry is really what you call thermal compressibility. Okay. So what is thermal compressibility? So thermal compressibility is a very interesting kind of a quantity in thermodynamics. You might have heard of what you call the laws, where you say, I think it's Boyle's law, where you say that if for a given substance you keep the temperature constant, then the pressure and the volume of that substance are inversely proportional to each other. In other words, if I take this duster, and the temperature of the environment is constant, okay, then the volume of the duster, volume means that how much space this occupies, and the pressure means that how much pressure I am exerting on this duster, are inversely proportional. In other words, the more volume you have, the less pressure I am going to apply. So if I am applying less pressure, I am going to have more volume, and if I am applying more pressure, okay, so I am applying what you call more pressure, so there is a less volume for the duster actually. Okay. So for a substance, so it's a kind of a well-known law that the volume is inversely proportional to the pressure actually. Okay, where the constant of the proportionality is temperature. Okay, so say K is temperature, and it's constant of proportionality. So it's a very well-known law. And it is temperature. Okay. Now, what I would like to do, I would like to define what you call the isothermal compressibility. So the chemist might have encountered this isothermal compressibility of substance as the ratio of the change in volume when the pressure is changing compared with the original volume of the substance actually. And I think a negative sign. Negative sign here. Negative sign here. And you denote isothermal compressibility by eta. So what is the definition of isothermal compressibility? So the isothermal compressibility for a substance is the ratio of the change in volume when the pressure is changing with the original volume. In other words, comparing that how the volume is changing when the pressure is changing, okay, with the original volume of the substance actually. So if you take this ratio, you call this as isothermal compressibility actually. Okay. So for example, let's do a little example. So for example, consider a substance. Let's take an example. So imagine that okay, so the example is that imagine you have, we denote volume V in cubic meters, okay, and say the temperature, say, so you have a volume of air actually, okay, so the volume of air at say 25 centigrade, okay, and say P is the pressure, okay, and you measure the pressure in kilopascals for example, so kilopascals, okay. So V is the volume of say air at say temperature 25, and P is the pressure of, what do you call, volume, the pressure at, what do you call, in kilopascal, okay, the pressure of the air. So how the volume and pressure are real actually, related with each other. So the volume and pressure are related with each other, say for example, by this equation 5.3 actually. So the 5.3 is the constant of the proportionality. Okay. So the volume of the air is related with the pressure by this equation actually. And what I want to do, I want to compute the isothermal compressibility. Okay. In other words, I want to know how much the volume of the substance is decreasing, or how fast the volume of the substance is decreasing as compared to the volume of the original volume of the substance actually. So you call that as isothermal compressibility. So isothermal compressibility once again measures that how fast the volume of the substance, any substance, so for example air here, is decreasing, okay, when the pressure is changing compared with the original volume of the air actually. Okay, we could take a container and let's talk about that. So you have this equation. Now let's compute for example this isothermal compressibility. In other words, let's compute that how fast the volume of the air will decrease when the pressure is say 50 kilopascal actually. Okay, so it's 50 kilopascal. So I want to know that how fast the volume of air when the temperature is 25 centigrade decrease when the pressure is 50 kilopascal. So for this you need to compute what you call the change in V with respect to P and substitute it into the formula. So what would be the dV by dP? So the dV by dP, if V is this, is going to be what? Minus 5.3 upon P square. In other words, you can write this as 5.3 P raised to minus 1 and then minus 1 multiplied by minus 1 minus 1, so it's going to be minus 5.3 P square actually. So the isothermal compressibility beta is going to be what? So it's going to be this, which is minus 5.3 P square divided by the volume, which is 5.3 divided by P, and I have a minus here, and then simplify this expression. So when you're going to simplify this expression, it's going to be 5.3 p square times p by 5.3. So the 5.3 and 5.3 will go away, so you're going to remain with 1 over p actually. So this is really compressibility rate. So 1 over p. So the beta is going to be then what? You just substitute the value. And once you substitute the value, you're going to get what? Either you can directly substitute values here, and if you wish you can substitute p equal to 50 here, so if you substitute say p equal to 1 over 50 here, so it's going to be 0.002. So what would be the units for it? So cubic, okay, it's going to be cubic per kilopascal per cubic meter. Cubic meter per kilopascal per cubic meter. Yes. Cubic meter per kilopascal per cubic meter actually. So this would be, what do you call it? This is the rate at which the volume will decrease as compared to the original volume when the pressure is increasing, okay, or when the pressure is 50 kilopascal actually. So this is what another example for thermal compressibility is. We can have, say, for example, another example from, let's take some examples from biology. Okay. So from biology we can have several examples. Okay. For example, these days the interesting problem that is going on to be to know that at what rate, you know, the number of patients of COVID-19 are increasing in Pakistan actually, or in Sindh, or in world, or in your particular region actually. So you want to model that rate actually, and one can model it through differential calculus, but it's going to involve some randomness actually. Okay, it's not that straightforward. Okay, but let's start talk about two examples from biology. Let's do example from biology. So the first example is, what do you call, say, rate of growth of a population actually. Rate of growth of population. Okay. So imagine you are talking about a region. Okay. And imagine you know that the number of people, or number of animals, or number of bacteria, or number of COVID patients, or whatever, okay, is n actually. And its population, and this n is equal to t. So the P of t is the population, so I can say that it's a population of, say, bacteria, animals, say, plants, say, viruses in your computer, Trojan horses in your computer, etc. So n is representing what you call the population of the bacteria, animals, planets in this region or your computer at time t. At time t. Okay. So you want to know that, okay, if I'm going from, say, time 1 to time 2, that what is the growth of the population, what is the growth of bacteria, animals, planets, viruses in this region between this time interval actually. So one way would be to talk about, say, average growth. So the average rate of growth, say, for example, average growth rate, if you are interested in, is going to be what? is going to be that, okay, you compute the population at time t2 and subtract the population at time t1 and divide it by the t2 minus t1. So this would be the average growth rate population. And what would be the instantaneous growth rate? Okay, the instantaneous growth rate. So for that, in other words, instantaneous growth rate is what? So take your average growth rate, but consider it in a small interval of time, in a really tiny interval of the time actually. So it's going to be the change in population in a smaller interval of the time when the time is changing, and the change in time is really tiny actually. So you want to consider what would be the change in population in this tiny amount of the time actually. So we call that rate as dp by, what do you call dt? Okay. So in other words, the way the population is changing instantaneously when the time is changing in a small quantity, in a really tiny small quantity. So this is what that you have. Okay. All right, for example, let's have an example. Let's take an example. So imagine this is a culture or a slide or some place. Okay? And when you started your observation, the initial population of this was n naught. Okay, so the initial population of this was n naught. And let's assume that the population doubles every second actually. The population of say bacteria doubles every second. The viruses in your computer doubles every second. That would be something scary. But let's assume that it doubles every second actually. So in other words, let's assume that population at time 1 is the double of the population at time 0. So this is the population at time 0 when you started your observation. This is going to be 2 and naught. So P of 2 is going to be 2 times of P of 1, so it's going to be 2 square and naught. So if you keep on generalizing it and you model it, so you're going to say that population at any time t, okay, is 2 raised to t, because think about it, if I take for example P of 3, so it's going to be 2 times of P of 2, so keeping in with this fashion is going to be 2 cube times of times n naught. Okay, so the P of t is going to be 2 to the t by the same fashion n naught. So this is, say for example, our model that models, what do you call, the situation that when the population of some bacteria or viruses is doubling actually at every single instant. Okay. At every single instant. So now I want to know how fast this population is changing. So now we would like to know that how fast this population is changing. So this is the formula for the population, but now you are interested in that, okay, you have this population at time t, but you want to know that how fast this population is changing. So if there is something dangerous and there is some dangerous virus, but it's slowing really slowly, so you will not worry much about it. But there is a dangerous virus, for example, and its population is increasing but rapidly, then you should worry about it actually. You should worry about it so that things can be done. Okay, so the lockdown can be done actually, something like that. So you want to know that, okay, how fast this population is changing actually. So for doing it, you need to do what? you need to compute the derivative of the p of t with respect to dt. So it's going to be the derivative of dt of the 2 raised to t times n naught. So n naught is a constant, you can pull it out, and then what remains is 2 raised to t actually. Okay? And then we know the formula that, okay, if you have the derivative with respect to dx of a to the x, so it's going to be a